welcome again to RF transceiver design. We are discussing a non-linearity in RF system. We have defined a gain compression in the last class. So, that is a 1 dB compression point and it is given by square root of 0.145 alpha 1 by alpha 3. So, the typical value is around minus 20 to 25 dB for this kind of for any RF system, and it can be improved by making the more better topology, circuit topology for any amplifier system. So, what are the attributes of compression that we will see in the next slide. So, frequency modulated signal, if there is a frequency modulated signal, if there is a frequency modulated signal, so what happens that only the your frequency is going to change, your amplitude will always be a constant. So, if you have any system where you are using a frequency modulated signal, then it does not contribute, means gain compression does not have any effect on detection, because ultimate aim of the RF receiver is to detect the signal with the correct information. Now, here there is no information lie in amplitude and gain compression is related to the amplitude. If we are using a frequency modulated signal, then we do not need to worry too much about the gain compression. So, that will tolerate the system. But let us say if you have a amplitude modulated signal, now in amplitude modulated signal, if there is some interferer, so this is a desired signal, and if there is a one, so at certain frequency omega naught there is a desired signal and some frequency omega 1, that is a undesired signal, that is called a blocker signal. So, what will happen when there is a very high amplitude blocker signal, due to the harmonics or it will try to add the non-linearity, or it will, let us say if you have a your amplitude is something like, so this is a desired amplitude, but in reality it will be distorted and your amplitude will change because of this blocker, and this will ultimately reduce the sensitivity, means amplitude of the signal will reduce the sensitivity of your receiver. That means it is a means it is a desensitizing your system, it is called a desensitizing the system. So, this phenomena of blocker making the system desensitized. So, because there is a input is going to come omega 1 as well as omega naught, because of this high amplitude your all the systems are considering the compression, and while recovering the signal there is a too much deviation in the amplitude that you will see. So, this phenomena is widely known as a desensitizing, and that is happening due to the blocker of the blocker of high amplitude, and it will also degrade the SNR, signal to noise ratio, it will degrade, and your noise figure means your requirement of sensitivity in receiver design will increase. And there is a some standards, in some of the standard even 50 to 60 dB blockers need to reject. So, you need to have a RF system, RF receiver which can block the blocker which is a 50 or 60 dB further, higher than your desired signal. So, what it means that your system, your receiver system should be much linear, so that this cannot corrupt your desired signal. So, these are the attributes for when you are designing the RF system or RF receiver. Then you should consider that there is a blocker of high amplitude which is out of band, and that, so there are two kinds of blockers that is possible, that is a in band blocker and out of band blocker. So, if you are in the ISM band for example, then in ISM band there is a blocker that is a in band, but if outside of the ISM band, if there is any blocker, that is a out of band blocker. So, there is a requirement of there are two kinds of blocker, in band and out of band. So, I will give one more example. Let us say if you have a 900 megahertz band and inside the band if there is a some bandwidth of megahertz that we have already seen in the last class, and if there is some blocker here, that is a in band. But out of the 900 megahertz, if there is a 2.4 gigahertz some blocker, that is a Wi-Fi band. So, that is called a out of band blocker. So, when you want to find out the non-linearity of by considering out of band or in band, there are different values that we can define. So, these are the two kinds of blocker. So, this is related to the if there is a single tone. Now, we will move to the another terminology, that is a intermodulation. So, if there is only single signal, so same thing has been written, if there is only single signal, then there is the possibility of harmonic distortion. So, that we have already seen gain compression, and blockers also can also add the harmonic distortion, and it will that large interferer, it is also in some of the places or books, it is blocker is also mentioned as an interferer. One more term that is that can also be added, that is a jammer, if it is jamming your current receiver. So, that is also one terminology is used in many RF system. So, ultimate aim of this all blockers are to desensitize your current receiver. So, this will come under the harmonic distortion because there is only single signal. Now, let us say if you have a two interferer signals. So, if you have more than one signal, and mostly this is considered as a two tone. So, if there is a two tone, let us say for example, if the omega 1 is the input frequency, omega 1 and omega 2. So, two tone is two frequency are applied. So, make sure that this is a near to each other. So, omega 1 and omega 2 are placed at very near to each other. Then if it is applied to non-linear system, you will have a multiplication of harmonics. So, n omega 1 n omega 2, that is a harmonics, and then you will have another term, that is n omega 1 minus omega 2 or omega 1 minus n omega 2. So, these terms is called a intermodulation product, because what exactly the definition, components means frequency components that are not harmonics of these frequencies. Let us say this frequency here means omega 1 and omega 2. So, here it is a frequency. So, the frequency component, that is frequency component that are not harmonics of this omega 1 omega 2 frequency are called intermodulation. And if I represent in terms of n and m, it is nothing but n omega 1 plus or minus m omega 2. So, this is n and plus or minus m omega 2, where n can vary from 1 to n, m can vary from 1 to n. So, this are called the intermodulation products, and we this intermodulation is occurring because of mixing inside the your nonlinear system, because two terms are mixing, and that is why you have a intermodulation that is happening. Now, we will try to analyze the intermodulation through the derivation. So, now if I have a yt, same we will consider yt, which is a alpha 1 xt plus alpha 2 x square t plus alpha 3 x cube t. Now, xt, your input function, has a two tone. So, xt, which is equal to a1 cos omega 1 t plus a2 cos omega 2 t. Because we have a two tone, so the first tone has a frequency of omega 1, it is a amplitude of a1, another tone it is a frequency of omega 2 and it is a amplitude of a2. Now, we try to put xt in this equation. So, we will get yt, which is alpha 1 a1 cos omega 1 t plus a2 cos omega 2 t plus alpha 2 a1 cos omega 1 t plus a2 cos omega 2 t square plus alpha 3 a1 cos omega 1 t plus a2 cos omega 2 t cube. Now, if we try to analyze, we are interested in frequency of 2 omega 1 plus or minus omega 2. So, if you try to expand this equation and square and cube you will do, you will get the term 2 omega 1 plus or minus omega 2 t. So, what is the term? 3 alpha 3 a1 cube, it is because we have a1 and a2 different. So, it is a a1 square a2 by 4. So, same thing we have already done in the gain compression, same thing. So, what will give you the cos 2 omega 1 plus omega 2 t plus 3, it is because we are already writing the third order term and 3 we have taken out. So, it is a cos 2 omega 1 minus omega 2 t. So, how this came? This will remain same, a1 cos omega 2, a2 cos omega 2 t, but when you try to make the square a1 square cos omega 2, so how generally it will be a plus b square, where a square plus 2ab plus b square will happen. So, because of this 2ab you will have a a1, means one is a a1 cos omega 1 t and another is a a2 cos omega. So, omega 1 minus omega 2 will come because of this, but because of this square you have a, because of this cube you will have a this component 2 omega 1 plus or 2 omega 1 plus or minus omega 2 t, and its amplitude is given by 3 alpha 3 a1 square a2 by 4, and you can also get a another term 2 omega 2 plus or minus omega 1. So, its amplitude will be same 3 alpha 3 a1 a2 square, because now we are interested for, so this is a a1 square and then there is a a2 square will come. So, you will get 3 alpha 3 a1 a2 square by 4, that is a same cos 2 omega 2 minus plus omega 1 t plus cos 2 omega 2 minus omega 1 t. So, when you try to expand this yt, we are interested in these two quantity omega 1 2 omega 1 plus or minus omega 2, and why we are interested for this quantity, we will take one example, we will get more idea that why we are only interested for this quantity. So, if you have a nonlinear amplifier and if you have given a two tone omega 1 omega 2, and for example this omega 1 is a 3, because we just want to analyze what are the different combination of omega is possible, and if we try to expand, if we try to see the output or the spectrum. So, the first component that you will get is omega 1 minus omega 2, and after very high frequency you will get omega 1 omega 2, and then there is a 2 omega 1 minus omega 2, this is 2 omega 2 minus omega 1, and again you will get omega 1 plus omega 2 t, and further you will also get a 2 omega 1 plus omega 2 and 2 omega 2 plus omega 1. So, what are the omega 1 omega 2 components? We will also write it down, omega 1 omega 2 component. So, that can be written as a alpha 1 a1. So, 1 is alpha 1 a1 from this, that is has a omega 1 plus 3 by 4 alpha 3 a1 cube. So, when you will have a cube term, then you will get the 3 by 4 alpha 3 a1 cube plus 3 by 4, here it is 3 by 2 alpha 3 a1 a2 square cos omega 1 t. Similarly, you will also get alpha 1 that is a2 plus 3 by 4 alpha 3 a2 cube plus 3 by 2 alpha 3 a1 square a2, that is cos omega 2 t. So, here how it is happening, that we as we have analyzed in the gain compression, similarly we will try to analyze the third order component also. And when we are trying to analyze third order component, what are the first order term which is added. So, in the first order there is a term which is added due to the cube, and as we have considered the higher orders also, then we are getting another component. So, there is a more components are added in the fundamental harmonics also. So, it will reduce the gain in your fundamental harmonics because of this alpha 3. And why we are considering the 2 omega 1 plus or minus 2 omega 2 or 2 omega 2 plus or minus omega 1, the most important part. So, if this frequency is a 3 hertz and if this frequency is a 4 hertz, then the first point, that is omega 2 minus omega 1, if we consider, that will be around 1 hertz. Then 3, and this is a 3 and 4, this is this will come as a 2, this is a 5, and then this is a 7, and again this is a 10 and 11. So, you can see that in this example we have considered omega 1 is equal to 3 and omega 2 is equal to 4. But if we consider omega 1 is equal to 2.4 gigahertz and omega 2 has a 2.41 gigahertz, there is a 100 megahertz difference, 2.4 and 2.41 gigahertz. Then omega 1 minus omega 2, you can consider it will be around 100 megahertz. It is a 100 megahertz. And if you find out the 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, so that will roughly come, this will come as a 2.39 gigahertz and this will come as a 2.42 gigahertz. And omega 1 plus omega 2 will be very far. So, it is a addition of these two, it is a 4.81. So, omega 1 plus omega 2 and 2 omega 1 plus omega 2, 2 omega 2 plus omega 1, these frequency are too far compared to this third order component, because this third order component 2 omega 1 plus or minus omega 2 will provide the very near. So, these components are near to the desired signal. Your omega 1 omega 2 are a desired signal and these tones are just coming near to the your fundamental frequency, and that might that will add the non-linearity. So, that this is not a desired tone and we need to analyze, because other things we can easily filter out, but we cannot filter out this easily because it is very near to the frequency of interest. So, that is why when we try to find out the intermodulation product, we need to consider the 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. So, we can also one more example. If this is your desired signal and these two tones are interfering, omega 1 and omega 2, and if this is the amplifier, this is the input to the amplifier, then there is a possibility that due to these two tone, which is a interferer, and that will coincide with your third order component might come at your desired frequency due to this two tone, omega 1 and omega 2. So, your 2 omega 1 minus omega 2 will lie in your desired frequency. So, you required your low noise amplifier should be as linear as possible, and your third order nonlinearity should be better, so that you can this amplitude third order component will be as small as possible. So, this is why we are studying the intermodulation, and it has a effect on the complete RF system. So, we will try to find the third order intercept point. Third order intercept point. So, what is happening? So, if we see the last slide, that the third order has an amplitude which is growing by cube. So, if A1 and A2 is equal to A, then this is going by cube, and first order is going by A. So, that is a alpha 1 A. So, we can plot the same, that is a 20 log alpha 1 A, and this is a third order plot, that is a 20 log 3 by 4 alpha 3 A cube. So, the slope of this will be the alpha 1, means that is a first order, and this is a third order. So, when we try to plot the amplitude of the first order, so this is amplitude of the first order, and when we plot the amplitude of the third order, and we start changing the input power or input amplitude, this output, so this is a output will also follow. So, the first order will follow, the slope of this is a first order, however, the slope of this is a third order. So, because the slope is a 3 times of this, at one point there is an intersection, that is a asymptotic expansion has been done, and the this is a point at which these both will intersect, and that point at the input side is called the IIP3. Because it is a input side, it is a input, and because it is intercepting, it is an intercept point, and why 3 is coming, because it is because of third order non-linearity. So, I just want to give one analogy, that if this is m omega 1 plus, means plus or minus n omega 2, how we will get it is third or second or first? We just do the addition of these two. So, it is nothing but m plus n. So, in our case it is a 2 omega 1 minus omega 2, 2 omega 2 minus omega 1. So, your m is equal to 2, your n is equal to 1. So, you are getting a m plus n which is equal to 3. So, that is why it is called a third order. If m is equal to 1, n is equal to 1, then it is a second order. So, it is a IIP2, IIP3. So, mostly we are interested for IIP3 because these two components are lying just as at the desired frequency. So, how we will find out that? We try to equate both, that is alpha 1 A IIP3. So, because we are interested to find the IIP3 point, that is 3 by 4 alpha 3 A cube IIP3. So, how this term came? So, this term came because of what we have considered 3 by 4 alpha 3, here A1 is equal to A2 is equal to A. We consider that amplitude of both the tone are same. So, if amplitude of the both the turn are same, it is a cube if you consider 2 omega 1 minus omega 2 or 2 omega 2 minus omega 1, it will remain same. So, the point at which this will intersect is nothing but the IIP3 point. That is why we have written AIIP3. So, we can write it down AIIP3, which is equal to square root of 4 by 3 alpha 1 by alpha 3. So, you can observe that this equation looks similar to the equation that we have derived for 1 dB compression point. So, we can also write A 1 dB, which is equal to 0.145 alpha 1 by alpha 3. If we just derive AIP3 by A 1 dB, you will get the value that is 4 by 0.145, and if you convert into the dB, it will roughly around 9.6 dB. So, your IIP3, what it says that there is a relation between your IIP3 and 1 dB compression point, and your IIP3 is 10 dB higher than your 1 dB compression point. So, your AIIP3, if we consider in dB, which is equal to A 1 dB plus 9.6 dB. So, it is 9.6 dB higher compared to the A 1 dB compression point. But in many cases there is a means in real scenario it might deviate. The deviation is because I will tell that when we try to find out the 1 dB compression point, we have only considered these two terms, but we have not considered this third term, and these terms is going to increase if we consider x raised to 4, x raised to 5, and this will also change your 1 dB compression point. So, this is by considering only the first two term we have find out, and that is why the relation here is 9.6 dB. So, this is a rough idea you will get the relation between IIP3 and 1 dB compression point. So, here one more analogy that you can add, that is, if this is a third order point and this is a first order point. So, this is a omega 1 omega 2 and this is a 2 omega 1 minus omega 2 2 omega 2 minus omega 1. Now, because when this is increasing one time, this is increasing the 3 times, because the amplitude is a thrice. When this is increasing, it is opposite. When this is increasing one time, I will try to erase. When this is increasing one time, this is increasing 3 times, 1 time and 3 times. So, what is the difference? I will write it down here. The difference in increment. So, if this is increasing the 3 times and this is increasing the 1 times, the difference. So, the difference in increment is a 3 minus 1, that is a 2 times. So, you can write, if this is a difference is defined as a delta p. If I will define the difference as a delta p, then I can write it down, that is a 2 times of A IIP3 minus A in 1. This is a very important equation. if you want to find out the third order intercept point, that your first order is when it is increasing one time, then your third order is increasing 3 times. So, the difference between 2, that is a delta p, is a 2 times a IIP3 minus a in 1. So, if we write it down, if we are interested to find the IIP3, so IIP3 which is equal to P in. So, because it is a difference, we can also represent in terms of power P in plus delta by 2. This is a very important equation. IIP3 of your system you can find out if you have given a 2 ton input, and if you know the input power, the difference of that 2 delta P by 2 means in the output, if you know the difference, then you can get the IIP3. So, you can also find out the IIP3 by using a spectrum analyzer, and you can also find out the IIP3 by plotting the few points at third order points and first order point, and then plotting asymptotically, and wherever it is intercept, that point is a intercept point. So, we will discuss further in more detail about IP3. We will try to take do one example to get the more idea about IP3 in the next class. Thank you.